Okay. Welcome back. So, today we're going to do a follow-up to the separable differential equations lecture. And there's a question I got last spring. And it's basically like, how do you resolve, plotting, like something like an implicit solution that comes out of these equations. For instance, for one of the examples, we end up getting the equation, let's see, we can find an example. Yeah, so we got an equation, sine of y plus e to the y is equal to x to the 6 minus x squared plus x plus c. And, presumably it's supposed to correspond to some sort of function, and the question is, how do you find out what that function is? The answer really comes down to something we learned out of Calculus 1, and I want to talk to you about that now. So why don't we go ahead and get started. Okay, so we're going to be talking about Newton's method today, and so let's go ahead and bring that up. Alright, now, Newton's method is a rather straightforward method. It's a method of finding roots to an equation. So you have some sort of continuous or differentiable function, and you want to be able to find out when it's zero. So Newton's method basically makes a tangent line for any guess you make on the curve. It makes a tangent line to that curve, follows it to zero, and then uses that x-coordinate as a starting point for the next guess. And you keep taking tangent lines over and over again until you hopefully converge. There's no guarantee you'll converge. Sometimes you do, and there's certain conditions that you can make guarantees for. But for an arbitrary function, there's really no guarantees. So here, I'm just giving an example of Newton's method without the differential equations overhead. And we're taking a look at y equals x squared minus 2. So this is the inline function I made in MATLAB. And basically the idea is that we're going to be looking for zeros of this function. So if I'm looking for a zero of this function, then that should be the square root of 2. Or minus the square root of 2, depending on where we start. What do you need? Well, you need the function's derivative, so that's going to be 2x, just because it's just x squared minus 2. And you need an initial guess. Well, 2 seems to be as good of a guess as any. Then, if you iterate, so for instance, I can iterate just one time and see what we get. So the first guess, using that slope method, was starting at the point 2 and x squared minus 2, which would be 2 again, so it would be 0.22. It found the slope, and it found a linearization, a tangent line, and set it equals 0, and then solved for x to find the next x coordinate. And that next x coordinate was 2.25. That's something you could do by hand. It shouldn't be too bad. And that's what this is doing. So first of all, it finds the y coordinate corresponding to the x guess, and then it makes the next x guess by calculating this. And it got this guy by basically making a linearization. So it takes the derivative of y x naught, and then this is a point slope form for a line. And so we have the x naught and y naught because we started with the x naught and we calculated the y naught. And then we just solve for this guy, x, and that gives you this. And so we can just go ahead and plug this in, and then that gives us our new x naught, and then we just repeat this over and over again. And this is called a for loop, and it goes from 1 to up to however many times iterate is. So I can say, for instance, make it go up to 3. So I say 3, and look, it does pretty good. I should say that what we got was not 2.25, but the next guess was 1.5, and if we square that, we get 2.25. I'm sure you guys could read this text. And now, so our next guess is 1.4142, and if you square that, it gives us 2.0000. And honestly, for our purposes, I think that's pretty close. It turns out that this would actually ultimately converge as we go off to infinity, yeah. So that's Newton's method, and that's me coding it up. So what does Newton's method have to do with solving an implicit equation? So if you look at an implicit equation, so this, for instance, is a solution to a differential equation. What was that differential equation? I put this in here, but you actually don't need it in my code, so it's kind of superfluous. But it's good for visual inspection. So basically, the differential equation we started with was minus x over y. And an implicit solution to this differential equation is x squared plus y squared is equal to c. But in this case, rather than having c as arbitrary, I just chose c to be 1. So ultimately that means that we're going to have a circle of radius 1. And so basically, this is an implicit solution to this differential equation when you set it equal to 0. So now the goal is to be able to figure out what all my y values should be. So we know what x's are. It's whatever we select them to be. And so we're going to choose x and fix it. And then we're going to do the Newton's method treating y as a variable, as the independent variable, and g as our dependent variable that we had back in Newton's method here. So we had x and y playing those roles, but now I have y and g playing those roles. And then I basically take the derivative of g with respect to y, and then I take a linearization and set it equals 0, etc. In fact, we even get 2y, which is exactly what we had previously. So I take an initial, so I fix x at -1, and I'm actually saying y of 0 should be 2 times sine of 0.5. This is maybe an overly accurate guess, and Newton's method would correct this guess later. But basically, remember that x's are fixed throughout here, and so we have a collection of x values ranging from x of 0 to x of 0 plus 2, so -1 up to 1, and we increment it at 0.01. So now I'm trying to find y, and so for each fixed x, I find a new y, and so that's what we do. So so essentially, yeah, okay. So basically, I'm just using that random guess we made up there. It might work for like some point, but other than that, we don't really know. And we just feed in these x values, and yeah, and so basically we find our we have a point y0, g0, and find the linearization there, and that's doing the same sort of thing that we were doing before. Remember, x is fixed for a lot of this, so basically our outer loop goes through x values, inner loop goes through our values for Newton's method. And so I iterate 10 times, and then I pick out something for y after using Newton's method, and then I record it. And so I put it in here. And this was our dummy variable, y values, which was a vector of zeros. Then once we're done, I plot them and see what we get. So I'm going to change the iterate to just being 1 time for each, and it'll probably pretty terrible. Remember, this should be a circle of radius 1. This actually was horrible. Start up here, and but then after we got to this point, it seems to do pretty good, actually, even with just 1 iteration. If I change it to, say, 5 iterations, let's see what happens. 5 iterations, yeah, it's a lot better. It looks a lot closer to 0, which is what it should be at that point. Changing it to 10 iterations, what do we get? Here. So it's practically perfect. It's practically a perfect circle. So that's what we expect. So yeah, so that's how you'd find solutions to iterates. That's how you'd iteratively find solutions to these implicit equations. So you basically fix an x, and then you run Newton's method on y on these implicit equations to help to find out what y should be for that particular value. But this was something we could solve already, and it was a good example because we knew it should be a circle. What I can do is I can go ahead and try a different value, a different function, and I haven't tried this before, so let's see what we get. So I'm going to make another implicit function, and this was the solution to one of our differential equations. And so yeah, let's see if we get anything. So what we had was sine of y plus e to the exponential of y, and then we have minus x to the 6 plus x squared minus x, and then we had a c in here, and so I'll just make c1. And now we're running x from -1 to 1 as before, because I have no other good choices for what x should be. And this could turn out to be rather horrible. Let's go ahead and take the derivative of g, and so instead of this, let me comment that out. When you comment something, it won't run it, so I'm just going to replace this with something else. So let's see. This is going to give me cosine of y plus exponential of y, and everything else is 0. Okay, good. Alright, so now let's go ahead and run it. Let's have fun and just start with 1, and we'll cross our fingers and hope something converges afterwards. Let's see. Boop. Okay, so that's a pretty curve. It actually is something that converges. It's not going crazy, it's not something insane. The values are small enough to be reasonable. Okay, so yeah. So this was one of the examples. It was the example where we had dy dx is equal to 6x to the 5th minus 2x plus 1 over cosine of y plus e to the y. That seems like a really crazy differential equation, and we solved it in like 2 seconds. And now with this, we can actually get a picture of what it should be. So that's nice. Let's see if we can improve this picture. Let's iterate 10 times. Let's see what we get. Okay, good. So we had previously some extra thing that blew up here, but now it's like going all the way down here. And now this is a nice smooth curve. So good. I'm going to assume this is the right curve. I have no idea what the curve should look like. But if it didn't look like this, we'd be pretty screwed. We'd have no way of actually finding a solution other than using Newton's method. There's a slight variation on Newton's method that uses secants rather than tangents, but truly, I mean, if Newton's method isn't ever going to converge, that probably wouldn't either. Okay, so there we go. And so that's a couple of good examples of how you can resolve these implicit equations. Now, again, this is all MATLAB stuff, and it's not part of the class, but I thought you might be interested in seeing how this goes. And I guess I'm really tired, and I'm gonna go in. This has been MATLAB at midnight, and yeah, have a good night.